So I assumed that you really didn't want to hear me talk for 2 hours about hyperalignment. Yeah, but so I prepared. I have another talk that I often give on a related topic, but this is sort of the other half of my career, which is how do we understand the representation of high-level vision, especially in the object vision pathway. And we have we've been thinking about this for a long time. And come to the conclusion that a lot of the way we think about the functional organization in ventral temporal cortex is wrong. Okay, so again, it's the same usual suspects who are working with this on me. I should have a picture here also of Ida Gobini, because she and I are doing a lot of this work together. So this is an outline for what I want to talk about. First, we'll talk about most models or discussion of the organization of ventral temporal cortex focuses on the neural representation of faces, bodies, and objects. And generally, it looks like the ventral temporal cortex is optimized for person perception. So it plays a very large role in social cognition. And we'll talk a little bit about some of the specialization. Is that me? This. It's from outside. Okay. Evidence that the ventral pathway is specialized for spatial perception, especially for face processing. But then I'll show you a variety of examples for why we think there are problems with this model. And specifically, there are two major types of problems. One is there's a big stimulus sampling bias, which is, and then the second is that the computational methods are inadequate to really understand what we think the organization in this area is. So first, let's talk about, in what way is the ventral temporal cortex optimized for person perception, and specifically for face perception. Now, this is a classic study from Simon Thorpe's lab, and it shows the saccadic reaction times, choice reaction time when subjects see a display with a face on one side and some other kind of object like a vehicle on the other. And the task is look at the face. These are natural scenes in complex backgrounds. And what they find is that when people are asked to look at the face, they have much faster saccades than if they're asked to look at the object, like the vehicle. And that they get reliably accuracies above chance as fast as 110 milliseconds after the stimulus onset. Now this, I think, still hasn't been fully digested. This is blazingly fast and doesn't make any sense when you look at things like the ERP literature, because the response to faces, the fastest evoked potential to faces has a latency of around 170 milliseconds. Maybe there's one at 110, but this is actually an eye movement, which takes an additional 20, 25 milliseconds to initiate after the face has been identified in 110 milliseconds. Now, face neurons in monkey cortex have a faster response latency than neurons that are selective for objects or places over here. So this is work from Bell et al. And then this is a study by Visconti Diolegio Costello and Gobini, where they took Simon Thorpe's method and they looked at saccades to familiar faces as compared to unfamiliar faces. So how quickly can people make a behavioral response that reflects that they've detected, in some sense, which face is familiar and which one is not? And when it's a familiar face, they have saccades that are reliably better than chance at about 180 milliseconds. Now this also just poses real challenge because the fastest evoked potential that distinguishes familiar from unfamiliar faces is at about 230 to 240 milliseconds. So that's inside the brain. But somehow the saccade is able to make that decision 50 milliseconds faster. Let's see, these early face selective neural responses are not affected by attention. I won't go into details on this. This is a study that we did using MEG. And then we know that faces break through interocular suppression using continuous flash suppression faster than that upright faces break through faster than inverted faces. So in this paradigm, different images are presented to the right and left eyes, and the image in one eye is a dynamic, rapidly changing stimulus that grabs the visual system, and the stimulus that's coming into the other eye, that's making it into the retina and getting into the visual cortex, is not consciously perceived. So the question is, how much processing is occurring for that stimulus that's been suppressed by interocular suppression, even though there's no conscious awareness of it? And that's usually indexed by looking at how fast does that suppressed stimulus break through the suppression. Because the only way it's going to break through is if something, it's somehow being processed at a subconscious level. And what, in this work by Shang He, they found that the upright faces broke through much faster than the inverted faces. So even though the face stimuli were subjectively invisible, if they were upright, they break through faster. Now, building on that, Gobini looked at whether or not faces that are looking at you break through faster than faces looking away from you, or do faces of friends break through faster than faces of strangers? And in both cases, she found that was true. So again, there's all this processing of faces that's super fast, much faster than for other objects, doesn't seem to be affected by attention, and even occurs without subjective awareness. So that suggests that this whole system for face processing is optimized for being very efficient and fast and not requiring awareness or attention. And then we know that the extrastriate cortex has a set of patches that respond more to faces than to other objects. So in the human brain, in posterior cortex is the fusiform face area, the occipital face area, and the STS face area that respond more to faces than objects. And then in studies in monkeys in which they did fMRI studies to look at whether or not there were patches of cortex that show a stronger response to faces than non-face objects, they also found these patches. And again, they found a set of patches that they find consistently across monkeys, starting posteriorly in PL, then the intermediate ML, MF, and then AL and AM areas. So there seems to be a system, a set of areas, fields of cortex, that are responding more to face and are playing a special role in face perception. So this is a nice story, and this is the dominant story in how ventral temporal cortex plays a role in face perception. First, face processing is fast, requires mental attention awareness, and it's mediated by this distributed neural system in both humans and monkeys that seems to be specialized for face perception. So why am I up here saying there's something wrong with this? This is a beautiful story, but there's a fly in the ointment. And so how many people recognize this? It's terrible. Mothra, this is Mothra. You have to go back and watch the movie Mothra. A big fly. So what's wrong with this story? Well, first of all, it's based on experiments that are designed to test focused hypotheses that are driven by the investigators' theories and notions, and necessarily you can't have subjects look at everything. You can't test the responses to everything. So people are looking at, is there some special system for face and person perception? So they look at people's responses to images of faces and bodies and things like that. It's natural. You have to make choices as an investigator. You have to select some stimuli. You can't show everything. But is there a problem with that? Well, now the sampling bias is that this whole system, this model, is based on studies that use still images. And necessarily, they use a limited range of categories, generally faces, bodies, and isolated single objects. The second problem is that the computational methods for data analysis and model are based on univariate contrasts. And they ask the wrong question. They ask, what is the function of an area? So when identifying a face area, they say, well, this area responds more to faces than everything else, so it must be specialized for faces. So that's its function. And that's a very impoverished way to think about the tuning function for a patch of cortex. And I'll go into details about why I think that's a problem. Now, how many of you, I'm sure most of you have seen these animations before, right? These are the hydrosymbol social animations. And what's the difference between what you see going on over here and what you see going on over here? Yeah. So these two triangles seem to be having a fight, right? So there's a narrative, a social narrative that you just spontaneously attribute to this motion stimulus. Whereas these triangles just seem to be bouncing around mechanically, and you don't attribute any kind of intention or social interaction to them. So these stimuli have been used in a lot of MRI studies, dating back to this work from UCL. Castelli was the first author in this paper that came out in 2000. And they found that medial prefrontal cortex and this posterior STS area responded more to the social animations than the random mechanical animations. Now, what people have overlooked when they look at these studies that there also is this other area here in the fusiform gyrus. It's even in the lateral fusiform gyrus, and the coordinates look really a lot like the coordinates for the face area. Now, the stimulus has no face, has no form in it at all. It's just triangles. So there's no face form in there, but there's social content. So what's that about? Now, in a follow-up study, Gobini et al., or in replication, used the same stimuli and found again that the posterior STS, and actually all along the STS, the response to the social animations was greater than the random animations, going into orbital frontal, inferior frontal cortex, and some pieces in medial prefrontal cortex. But it extends down into the fusiform cortex. And this actually has been shown repeatedly. And in a study by Schultz at Yale, he did the face localizer and the social animations and showed that the activations for social animations and the face localizer overlap. So in the same study by Gobini, she also had people looking at point light displays of motion and showed what others have shown, which is that these point light displays of motion also evoke a strong response as compared to random motions or scrambled motions in lateral fusiform cortex. So there is this piece of cortex that is really close to or overlapping or identical to the face and body areas in fusiform cortex, but it's responding when the stimuli contain no biological form like triangles, or only have biological form that's inferred from the motion in point light displays. So the idea that this area is sensitive to the form of faces and bodies is belied by these studies. Now, making this matter even more difficult is the work from another Schultz at Yale, working with Greg McCarthy. And they had subjects looking at videos of industrial robots doing robotic things, building stuff, okay? And they had some robots that looked kind of animal-like and some robots that didn't have any look at all animal-like. And they were either doing random motions, or they're doing, they had a more goal-oriented motion. And what they found was when people were looking at robots performing goal-oriented actions, they got all this activity in ventral temporal cortex, including lateral fusiform cortex. So I don't have one of their videos. I just pulled this video off the web of something that's putting fan blades in a fan. It's a three-armed thing, but this is the kind of thing, when people see something like this, it activates the same, these same cortical fields in ventral temporal cortex that are associated with perception of biological form, like faces and bodies. So this is a problem. Now, the next study I want to show is the study that I talked about in the last talk by Sam Nastase, where it has people looking at these videos of animals doing different kinds of actions. So here we have ants and seagulls and baboons, and they're all running, okay? And now there's the gorilla, the hummingbird, and the caterpillar. They're all eating. And you can also have primates doing different things. So these are all primates. So there's a baboon running and a gorilla eating and a couple of baboons fighting. So now they share the taxonomic category and they don't share the action category. And here are 3 species of insect. I love these videos. That's why I show them so much. Because here's a ladybug fighting with an ant. And here's the caterpillar eating, and here's some kind of beetle running across the ground. So what, in this study, what the subject had to attend to either the action or the taxonomic category. And with each new stimulus, they would indicate whether or not, in some blocks, they would indicate if the action was the same as the previous action depicted, or was the taxonomic category the same. And these are broad taxonomic categories: insects, or birds, or ungulates, or primates. And then he analyzed this using representational similarity analysis. And he broke this down into 2 target or model similarity structures. In one, it's looking, it's saying, are the responses to the same taxonomic category more similar than responses to different taxonomic categories? And the other, this one over here, they're asking, are the responses to the same action more similar than responses to different actions? So to what extent are the patterns of response more similar for primates as compared to primates as in contrast to primates versus insects? The other is, how much are the patterns of response more similar for eating versus eating as compared to eating versus fighting? Okay? And it's a complicated paper. I hope it gets published soon. But what I want to point out here in the context of this talk is something that really surprised us, and that is that this model similarity structure was a much better predictor of the representational geometry than the taxonomic category. We've been laboring away studying taxonomic category for years, and now Sam comes along and shows us that that's a small part of the story. The big part of the story about what's going on in the brain is what is the response to the behavior you're viewing rather than what is the type of animal you're looking at. So this shows the variance accounted for, partial R squared, accounted for by the behavioral model and the taxonomy model. So you can see the histograms, the bars for the behavioral model are much higher everywhere. Oh, geez, Louise. In all these different brain areas, VT is ventral temporal cortex. Oh, geez, I'm sorry. There, okay. Okay, we good? Are we good? Yeah, we're good, okay. So the amount of variance explained is much higher. It's over twice as much variance as accounted for, but even in ventral temporal cortex. Now, this is something that's really surprising, and people are having a hard time accepting it, that in this particular study, we're finding that the representational geometry reflects representation of behavior, the actions of animals we're looking at, more than the type of action. So motion more than form, but a specific kind of motion that depicts the intentional behavior. Now, this is now a study of responses to dynamic natural movies that Brian Russ and David Leopold have been conducting for several years now at NIH. And so they have regressors from their movies about when are there faces in the movies and what is the amount of motion energy in the movie, and how good are how much variance is accounted for by the presence of faces, how much variance is accounted for by motion. And you can see this is much redder. So the motion is accounting for much more variance than the presence of faces. Now here are the face patches. So this actually is a very nice face patch localizer, just having the monkeys watch movies of other monkeys doing monkey things. And they can identify, here's PL, ML, AL, in the face patch system. But if you look at the variance accounted for in PL, ML, MF, AL, AM, the amount of variance that's accounted for by motion is much more than the amount of variance accounted for by the presence of faces. So again, their results don't contradict the earlier results showing that there are face patches that are more responsive to faces than other stimuli. What they're showing is that the response tuning functions in these patches is actually reflecting more the motion than the presence of faces. It reflects both, okay? You have to keep this in mind, that I'm not saying it's not either or. It's both, but one is more than the other. And they ran a control that shows that the type of motion is biological motion. It's not simple motion energy, because when they had videos that had a lot of motion energy, but with no animals, they didn't see this kind of effect at all. It was only the response to the biological motion of the monkeys that showed this. So, here are two more pieces of evidence that in the ventral temporal cortex in humans, in the face patch system in monkeys, it seems to be responding more to action and behavior, or more strongly representing action and behavior than it does form, even though the models I've talked about before are all focused on the representation of the form of faces and bodies. Now here's another study by Fairhall and Gobini that's also under review, where they had congenitally blind subjects listening to voices. And they looked at whether they could decode the emotional content in the voices, and where in the brain could they decode that information carried by the voices. And what this shows is that in the FFA, in the blind subjects, you can decode the emotional content of voices. So these are people who have never seen a face. It's impossible to identify their face area because you can't do a localizer study with them. But whatever that patch of cortex is in lateral fusiform cortex that has been deprived of visual input, the function it's assuming is a function for representing information from voices about other people. Okay? So again, it's just dissociating the representation of form, facial form, body form, from the representation of social content as conveyed by voices or behavior or the motion of abstract animations. So lateral fusiform gyrus is evoked or modulated by moving triangles in the hydrosymbol animations, moving points of light and point light displays of biological motion, industrial robots that have no resemblance to biological entities. It responds more to animal behavior than it does to animal form, or represents more strongly. And it can represent voices in the congenitally blind. So the sampling bias for previous experiments that used only still images of limited categories of faces, certain types of animals, and bodies has restricted the understanding of the functional architecture. So what is represented in diffusive cortex? Is it animate as compared to inanimate entities, or is it agency? So let's address this first question first. So is the animate-inanimate distinction the major large-scale feature here? So it doesn't have to do with the form of faces, the form of bodies. It has to do with, are we looking, is the subject perceiving, representing animate entities? And this has an old history too. So in the reanalysis of our 2001 data on representation of faces and objects in ventral temporal cortex, Alice O'Toole and Hervé Abdi did a similarity structure analysis and showed that the representation of faces in cats was distinct from the representation of the inanimate categories. There's this beautiful study by Rusbek-Kiani looking at single unit response, population responses using single unit recording in IT cortex of monkeys, and showing that the population responses show a similarity structure where the major distinction is between animate and inanimate. So there are these animate categories of different kinds of faces and bodies. And Kriegis-Korte took the data of Kiani and then got some fMRI data using the same stimuli and showed that the biggest distinction in the representational space in human ventral temporal cortex also was the distinction between animate and inanimate. So that seems to be, and then in the paper by Grill-Spector and Weiner, they hypothesized that there are these nested representational distinctions in ventral temporal cortex, and the overarching one is animate versus inanimate. Animate being lateral, inanimate being more medial, and then you have representation of faces, body parts, eyes, and things like that nested within the animate domain. Now, the problem, this is a nice story too, animate versus inanimate. This is, again, is dominant, and if you hear other speakers, they're going to talk about that as a major organizing principle in ventral temporal cortex. Andy Connolly ran a study in our lab where he looked at the representation of these 6 species of animal, 2 species of insect, 2 species of bird, 2 species of primate. And he found the dominant dimension in the representational geometry had primates on one end and bugs on the other and birds in the middle. So this, he called this the Animus E continuum because the bugs were on one end. And if you look at the contrast of primates versus bugs, okay, in the pattern of response, this is a univariate contrast. The primates evoke stronger responses laterally, and the bugs evoke stronger responses medially. So it's blue here because it's lower than the response to primates. So this topography, this univariate map, looks exactly the same as the topography of faces versus objects in the same subjects. So this difference between primates and bugs looks like animate versus inanimate, but nobody in his right mind would say that insects are inanimate. It's just that we think about bugs very differently from how we think about primates and mammals and even birds. So Longshot did a follow-up study where he had primates, mammals, these are cats and giraffes, birds, he had lobsters, stingrays, ladybugs, and clownfish, and then hammers and keys. And found the Animus E continuum, again, with the primates on one end, and the lower order things like bugs and fish on the bottom, and the birds and non-primate mammals in between. But the keys and the hammers really overlap with the low Animus E entities. So we thought, when we set this experiment up, that we were going to show that all the animate things were on one end, with an Animus E continuum, then there's going to be a big gap with the inanimate things way over on the other end, replicating the animate versus inanimate distinction. Instead, we got this result, which was really surprising, but suggesting that really the Animus E continuum the animate-inanimate is really a special case of the Animus E continuum and only reflects the distinction between objects and the higher order animals, like primates and mammals and birds, and not the lower order, but equally animate animals. And again, the topography for the primates versus objects is exactly the same as the topography for the Animus E continuum of the animals other than primates, and not including the keys. So this suggests that the animate-inanimate dichotomy is actually a special case of a broader principle, the Animus E continuum. And the Animus E continuum actually has a very deep intellectual history. Aristotle, in his treatise on the soul, talks about an Animus E continuum, starting with low-level things like clams, and then proceeding upwards to humans, but then humans are superseded by the gods. And actually, Animus E hierarchies play a role in linguistics, too. So people use different linguistic grammatical forms in many languages for things that are high Animus E versus low Animus E. And we even do that. So if we're talking about people, we always use he or she. But if you talk about things like bugs, you're very comfortable saying it, right? And that's this conditioning of grammar based on the Animus E continuum is even stronger in other languages. And then there's also something called the Great Chain of Being, which is also the Animus E continuum, which is considered another organizing principle in thinking around the late 19th century. So is the Animus E continuum the dominant organizing principle of ventral temporal cortex? Well, there's some problems with that too. So what is the Animus E continuum? So high Animus E things have more complex internal states that are driving their behavior. So it's a more complex level of agency. So is it the level of agency in the stimulus that is being reflected by this pattern of activity in ventral temporal cortex? So Gobini, proposed that in 2007, but then in a later paper where she had people looking at robots and that she found the same type of distinction, she says it's the representation of agency that's independently of whether the agent is living or not. So it can be agency in non-living robots. And Schultz and McCarthy come to similar conclusions in their paper. So is this it? Are we starting to narrow it, close in on what is the organizing principle? It's not faces versus non-faces. It's not animate versus inanimate. Is it the level of agency, the sort of natural perception of whether something is agentic? Well, I'm not satisfied with that either. And so now I want to have a little digression. I said I wouldn't talk about hyperalignment, but I talk about here, it comes from the work on hyperalignment. So again, this is the patterns of response while people are watching Indiana Jones. And the idea is that with each new time point, we have a different, a new vector. We've measured a new vector in the representational space. And that we derive this transformation matrix so that we can now have a common model space for responses to the movie. Now, there are two important things here that I want you to keep in mind. The first is that we're using a very different kind of stimulus. So instead of having a limited number of categories that we pre-selected based on our hypotheses, we just let Steven Spielberg make all of our choices for us. And people watch the full movies. And the second is that we're deriving this common space that's high dimensional. So how high dimensional is the space in ventral temporal cortex that captures the variety of responses to a more natural movie? So when we look at between subject classification performance for the top 5 PCs, so we did a principal components analysis and reduced the number of dimensions. When we look at just the top 5 dimensions, classification performance is down below 50%. Then it jumps up to around 62% with 10. And you really have to get up to over 30 before it's starting to show optimal performance of about 68% accuracy. So we can reduce the space from 1,000 voxels or 1,000 dimensions down to about 30 or so dimensions and capture all the variety of responses to the movie in that space. But it's not 2, it's not 10. Now the Animus E continuum, or the animate-inanimate distinction, is a single dimension. That would be a one-dimensional space, okay? So that one-dimensional space is not capturing the variety of responses in ventral temporal cortex. We need more than 30. Now we toyed briefly with the idea of saying, because it's pretty arbitrary where we say how many dimensions do we really need, right? So we thought we were going to just say 42. But how many of you know that, where the number 42 comes from? There we go. Mark's hand went right up. Hitchhiker's Guide to the Galaxy. So I think the magic number might be 42, but we're not sure about that. So that means that these low-dimensional spaces, like the Animus E continuum, don't account for very much of the variance. Now, when we look at the topographies with these PCs in ventral temporal cortex, the first PC is just picking off these 2 little spots, or just a couple little spots here. These are inside the FFA, but they're a very small part of the FFA. We don't really know what this PC is, but it accounts for a lot of the variance in responses to the movie. Now, this seems to have the animate versus inanimate, lateral versus ventral distinction in PC2. But you don't really see face areas in these PCs. So this shows the location of the face areas in these 2 subjects, superimposed on these maps of the PC weights, these topographic basis functions. And you can see that none of these top PCs is picking out the face area as something that's distinctively different from the rest of ventral temporal cortex. You can derive that as a weighted sum of these topographic basis functions and then get a very nice prediction of the location of the face areas based on a weighted sum. So maybe we just had the dimensions rotated the wrong way, and if we rotated them, so we picked up that particular dimension that has dominated the discussion of the functional organization of ventral temporal cortex, we find that was dominant. So we did that. We looked at how much variance is accounted for by this dimension, accounted for by faces versus objects, or the Animus E continuum. So this shows the variance accounted for by the first PC, second, up to 35 PCs. So the first one is about 21%. The 1D model, faces versus object linear discriminant, accounts for about 7 to 8%, okay? So the face versus object linear discriminant accounts for 7% of the variance, less than 20% of the variance accounted for by the first 3 PCs in this complicated space, and less than 13% of the variance accounted for by all 35 PCs. So it's a much more complicated space than is captured by something like faces versus objects, or animate versus inanimate, or the Animus E continuum. A single dimension just isn't accounting for very much. So let me try to drive this home a little bit and bring back the idea of stimulus sampling bias. Because remember, what we're accounting for here now is the responses to the movie. We're not accounting for responses to still images. If we look back at our data from Long Shaw's paper, where he did have still images of these 10 animal species and hammers and keys, and we do a scatter plot of the variance accounted for, the first dimension accounts for a much larger portion of the variance, okay? And this first dimension has the topography of the animate-inanimate distinction, or the Animus E continuum. So when you look at the variety of responses to still images, that particular dimension is accounting for more of the variance. But as soon as you use a more natural dynamic stimulus, it's a much smaller portion of the variance. And even in that study, the first PC captured the between-class distinctions. So that's primates versus lower-order mammals versus birds versus fish versus bugs, okay? But did not capture the within class, so people versus chimpanzees or warblers versus pelicans. Those within class distinctions were only captured by the lower order PCs. So you need a high dimensional space, even in that representational space defined by responses to still images, to capture those finer distinctions. So is the Animus E continuum, so varying levels of agentic complexity, the dominant organizing principle for representation ventral temporal cortex? Not exactly. The Animus E continuum face-object distinctions, which are really collinear, account for only a small portion of variance in responses to a rich natural dynamic stimulus. And the Animus E continuum and face-object distinctions account only for coarse but not fine-grained distinctions in this representational space. So let me summarize what I think what I've been trying to say here. First of all, there's a stimulus sampling bias. So studies have been dominated by looking at the responses to still images from limited pre-selected categories like faces and hands and bodies. I regret using Chiani's stimuli because this is a very rich stimulus set of still images as compared to these kinds of dynamic stimuli, like the hydrostimal animations, robots, or behaving animals. So these category-selected regions have more complex tuning functions that suggest they play more diverse roles in person perception. And the representational geometry is dominated by the representation of behavior, not by form. And the animate principle is not the principal dimension that characterizes the coarse lateral to medial topography in ventral temporal cortex. So, in a sense, this is like the blind men and the elephant. Now, the legend of the blind men and the elephant is 6 blind men are sitting by a river and they sense the presence of something large in their midst. So they go to investigate. They can't see what it is, so they have to touch it. So one blind man touches the tusk and says it's a spear. Another one touches the tail and says it's a rope. Another one touches the leg and says it's a tree. Another one touches the side and says it's a wall, etc. Now, all of those guesses make sense from what they are able to obtain from their sense of touch. But because they can't see the whole animal, and they can't put all those features together into the totality of an elephant. And in a sense, when we think about ventral temporal cortex and try to approach that with experiments based on limited stimulus sets with limited computational methods, it's like being blind because we don't have adequate stimulus sets, we don't have adequate computational methods to see the totality of ventral temporal cortex. That yes, things like the Animus E continuum, domain specificity, animate versus inanimate, category selective regions, all those things exist in ventral temporal cortex, but they account for only a small portion of what's going on there in ventral temporal cortex. And you need better designed experiments with natural, richer stimulus sets and computational methods that let you model it as a high dimensional space rather than stimulus selective regions. So the computational methods are inadequate because they use univariate statistics. They search for the function of an area rather than try to analyze what is the representational space in an area. Whereas multivariate methods like pattern classification, representational similarity analysis, hyperalignment, they model the functional architecture as a high dimensional representational space. And the topographies for these dimensions are multiplexed and overlapping. So instead of looking for an area, we look for a variety of topographies that are multiplexed with complex tuning functions at any given location. And this kind of a model can account for category selective regions as well as the fine-grained patterns that carry fine distinctions in these areas. So that's what I want to say, and I want to say thank you for your attention. That.
Everybody knows the mantra stimulus. Any hands up in the air here?
You're intimidated. Okay, there we go.
Hi. Might sound a little stupid or odd, but do you think this contingency could also be related to the value that humans usually ascribe to these objects? You know, that like a mammal or something that is more familiar to us that we ascribe
Yeah.
a higher value, like emotional value?
Yeah, so, we have not done a systematic analysis of exactly what is the Animus E continuum. You know, one hypothesis is it has to do with complexity of agentic behavior. But familiarity clearly plays a role. So for example, the cats are much higher in this Animus E continuum than giraffes, right? And we're much more familiar with cats because we live with them. So we think that familiarity probably plays a role. And value, I mean, I'm not sure exactly, you know, but yeah, how important do we think, you know, cats are as compared to giraffes or fish? Yeah. So that needs to be systematically analyzed. I'm still pretty comfortable with the complexity of agentic behavior as a good initial hypothesis. Yeah.
Hi, I still have a question on hyperalignment. I'm sorry.
They just keep pulling me back in.
So I wonder, so if I'm really interested in the individual difference.
Pardon me?
Individual difference.
Individual differences?
Yeah. If,
Okay.
If
Yeah.
I'm really interested in this domain, then is the hyperalignment still suitable? Because the way I understand it is that it diminishes the individual difference in the functional activity pattern.
So thanks for asking that question, because I was, you know, this is something that people always bring up, which is, can we start to look at individual differences in the common model framework? And the purpose of that project, building the common model, was to find what's common across brains. And we succeeded in finding a lot more commonality than we even expected. Does that mean that we've eliminated differences, or are there still differences? And so we're starting to analyze that systematically now. And there's a graduate student in the laboratory who's looking specifically at that. And the first question he asked is, are there reliable individual differences between subjects based on their representational geometry or based on their patterns of functional connectivity? And so you can get an index of how similar two subjects are by vectorizing all the functional connectivity vectors or vectorizing all the representational geometry vectors, and then just looking at the correlation between subjects as a similarity. And so some subjects are more similar than others. So now we have a subject similarity matrix. Some subjects are similar, some subjects are very different. And that subject similarity matrix is highly reliable across subjects. And so we thought, well, it should be less reliable after hyperalignment because we've eliminated a lot of the sources of inter-subject difference, like anatomical variability. We've tried to take that out of the equation. And actually, the individual differences are more reliable after hyperalignment than before, which is surprising. And so we think that, what we're finding is that that somehow this method, we don't understand why yet, is factoring out individual differences that we're not interested in that have to do with differences in the locations of areas and sulcal folding and things like tidal folding. Take all that out, and we're getting a more pure measure of differences in functional architecture, either representational geometry or functional connectivity. And we're actually finding clear differences between subjects. And so now we're looking at whether, Fei Long, is looking at whether these differences are related to individual differences in things like task performance, IQ, and we don't have an answer yet. But yeah, so that's so we're actually really excited that this is going to be a way of getting a purer measure of individual differences in functional architecture and factors out anatomy.
Hi. This idea of multidimensionality is great, and I think a lot of people are moving into it. Even Alfonso will be moving into it, I think. But what strikes me is that when you look at the neuropsychological literature, category specificity, and you use images of animals, and those images of animals include primates, monkeys, they include bugs, and they are compared against keys and hammers. And what you see is a divide that is more about category or domain, if you will. So why don't we see category specific, or if you will, I don't know, semantic deficits that follow this type of dimension or other dimensions that could be underlying the organization at the VT, but we see deficits that actually are in the divide between animals, tools,
I think that if you go back to those studies, you'll find that they're dominated by pictures of mammals and mammals and birds, mainly mammals. Very few bugs are in them. And no study before ours has looked at the difference between the responses to mammals versus bugs. So they lump them all together. And so if you lump them all together, you're going to get, the average is going to look like the responses to higher order animacy. And that's why it looks categorical.
So you're making a strong claim that if you were so you're making a strong claim that if you were to go back to any of these patients, and if we were, say, category specific patient that has issues with, is impaired at recognizing animals, but not the typical way of looking at, not other categories. If we were to analyze this patient, and if you were to look at comparisons between bugs and mammals, you're making the claim that this person would actually be okay with bugs, but not with
Yeah.
or at least you would see that
I mean,
divide.
I'm just saying that's what we find. When we look at primates versus bugs, we get a topography that looks just like mammals versus objects. So I mean, if that's reliable, then you should be able to see that in other data sets if they were broken down according to those distinctions.
Yeah, so I have just like super general question. So I was just wondering to what extent your methods can be informative in how people learn these representations.
Yeah. Yeah, so we haven't done that yet, okay? Now, in Sam Nastase's study with the animal behavior and taxa, he had subjects attending either to the animal behavior, saying, is this a repetition of behavior, or attending to the animal taxa, saying, is this a representation of animal type? And when they did that, the representational geometry warped. So the distinctions that were attended became greater, the distinctions that were unattended became smaller. So we know that attention will affect these geometries on a short time scale. And we assume that learning will affect these dimensions in a more enduring way. And one study I would love to do, and I shouldn't tell you because I want to do it, and now someone else is going to do it. I would love to get a group of entomologists who study insect behavior, especially complex social insect behavior, and see if their representation of insects versus birds and primates is different, because I would suspect that people who study termites or honeybees are going to have a much different understanding of how complex those animals are than the average person.
It seems to me, looking at your stuff, an interesting question might be whether you can also build representational spaces, maybe not the right term for it, but a vector that also includes process and function. That is, this map isn't going to tell us how we do calculus.
Right.
And yet your representational space for all of these concrete out of the things out there in the external world manages to populate the majority of Cortex.
Right.
And clearly we know that Cortex has segregation of different kinds of function. I wonder whether you've thought about building an extended representational space that also includes process.
Yeah. So we have to kind of work on the vocabulary. We started saying representational space because we were using representation of visual categories or auditory categories, things like that, or visual auditory features. We could warp that to say we're talking about the representation of addition versus subtraction, or logic versus estimation, or something like that. But I don't like, it would be better to come up with a different term to say that we're not just talking about the representation of a process, we're talking about the execution of processes.
We can forget the term, but think about the general geometric interpretation.
Yeah.
Extended to other dimensions.
Yeah. And the other thing that that brings up is what the model as I presented it is kind of it doesn't have time built into it. And so these processes unfold over time. And because we're using fMRI, and fMRI tends to be sort of a static picture of brain activity because of the temporal characteristics of the hemodynamic responses, we don't take time into account adequately. And I think that extending these ideas into modalities like MEG and EEG will force us to start thinking about how processes unfold with time, and how we can model these temporal processes in a common space.
We've spent in my lab time thinking about Markov processes and trying to look through we're looking for, but transitions between states and a trajectory through some sort of a state space. And when I'm thinking about it in the context of your data, it's a little bit contaminated by the fact that the way you're making these things is already built-in trajectory that's informed by Steven Spielberg, right?
Yeah.
What follows what, and to go and unpack that when you're outside of a resting state would be kind of tough, I think.
Unpack the
this notion of a trajectory through these spaces of a time dimension, right? The time dimension is enforced by the nature of how you actually build these models.
Yeah, and so let's just say it's a real challenge.
Others? I imagine what's happening is everybody's just dying to get their hands on the lab right now, right? Because you all want to do this yourself, so this is great.
So that's next, right?
Exactly. Next.
Starting at 4 o'clock?
Starting at 4 o'clock, yes. And Swaroop, I guess, is going to be running that. I believe that everybody has the data that was downloaded. Anybody have trouble with that? I have a hard disk which has it on it in both PC format and Mac format, and the virtual machine and everything. Okay, good. All right. Excellent. Thank you so much, Jim, for
Well, my pleasure. Thank you for inviting me.
finishing up our course with us.